Let's talk about trees. Rooted trees are similar to the trees you saw before, except for that they also have a value at the root of every tree. So previously I said that trees either have branches or they were a leaf value. And this was an example, where we had a tree that looked like that. And rooted trees have both branches and a root value. So a rooted tree would look like this. This is a regular tree with just values at the leaves. This is a rooted tree with a value at the root. And since there's a value at the root, and this branch is a tree, this is also a rooted tree with a value at its root. And this one has a value at its root. And so you get values everywhere. A rooted tree has a value root. So a rooted tree will be a data abstraction that combines a root value and a sequence of branches. And those branches are also rooted trees. A rooted tree with 0 branches is called a leaf. So there's a leaf. It has this root value of 1 and no branches below it. And the root values of subtrees usually have lots of other names. So within a rooted tree, you can have a subtree that looks like this. So this is a branch of the whole tree. And it has a root value 3. And that's often called a node value or a node. So there's lots of different terminology for trees because they're so fundamental to computing. So the next thing we'll do is develop a data abstraction for the rooted tree. We're going to define rooted as a constructor that takes the root value and a sequence of branches. It checks and makes sure that each branch is also a rooted tree, and then combines the value and the list of branches. The root of the tree is just the element at index 0. The branches are all of the other elements. Using slice notation, that's the rest of the elements in the tree. And if you want to know whether something is rooted or not, you just check and make sure that it's a list, has at least one element, and that all of its branches are rooted trees as well. If all of that is the case, then you return, yes, it's rooted. And a rooted tree, according to this implementation, is a root value and a sequence of branches. And all of those are rooted trees. So if I have a picture that looks like this, I can translate it into a program that looks like this. It's a rooted tree with 3 as the root value and 2 branches here and here. This left branch has a root value of 1 and no additional branches, which is this line. The right branch here has a root value of 2 and 2 branches, each of which are leaves with a value of 1. The way that this gets represented in Python, according to this implementation, is as a bunch of nested lists. So you might say, oh, isn't that some sort of tree without roots? Well, it just depends on how you're treating your data. So if you treat this according to the data abstraction and use only root and branches to access the elements of this, then it will behave just like the rooted tree that I described. Let's see if we can put this to use. So here's my rooted tree data abstraction and my abstraction barrier. Let's just first make sure that this all works. So it should be able to make a rooted tree that's just a leaf, like that, and that works fine. And I can put this leaf inside a larger rooted tree, which has not 1, but 2 branches. And it looks like that. Okay, that's not a very interesting tree. What's interesting is if we can illustrate the structure of a tree recursive process using a rooted tree. And so, for instance, if I want to build a tree out of Fibonacci numbers, with the nth Fibonacci number at the top, I could write the following. If n is 0, or n is 1, then I return a rooted tree with n and no branches. So that's a leaf value that's a base case for the Fibonacci sequence. Otherwise, I compute both the left and the right branches, which are respectively the fib tree n-2 and the fib tree n-1. So those are the last two values in the Fibonacci sequence, and the trees below them will show the structure of how they're computed. Now we actually have to figure out what's the root value. And the root value is what you get by adding together the root on the left and the root on the right. Finally, I return a rooted tree with this root value that's the nth Fibonacci number and the branches left and right. By calling fib tree on a base case, I just see something very simple. But if I call it on a recursive case, I see the structure of the whole Fibonacci tree, where 5 is the sum of 2 and 3, and 2 is the sum of 1 and 1, and 3 is the sum of 1 and 2, etc. all the way down. So this is an illustration of all the computation that goes into a recursive tree Fibonacci function. So that's interesting. Let's see if we can do partitions using trees. I'm going to go grab my old partitions definition, but now I'm going to compute a partition tree. So we're going to return a tree of the partitions of an integer. And that means we're not going to have any linked lists at all, but we will have to ask the same questions. So what happens in the base cases? Well, we have to decide how we're going to represent this tree. Let's have at the leaves of the tree just true and false to tell us whether we successfully partitioned in or not. So I could create a rooted tree that says, yes, I can partition it that way. In these cases, I return a rooted tree that says, no, it's impossible to partition n less than 0 or partition a positive n with m equal to 0. Okay, so that basically is a description of the base cases using a rooted tree. Next, we'll want to make recursive calls based on whether we want to use at least one m or not. So let's say yes is a partition tree, which makes the recursive call with n minus m. No is a partition tree that makes a recursive call with m minus 1. And then finally, I'll just return a rooted tree with m at the root to tell me what part I'm considering. And the branches will be yes and no. So what does a partition tree do? Well, it illustrates all of the different choices that I have along the way, and which ones actually managed to partition and which ones didn't. So we get false and true at the leaves. And this is a full illustration of all the computation that went into the partition tree in order to figure out what the partitions were. But it's hard to read, so let's fix that. Let's print the partitions that are encoded in this tree. And we'll do it by walking along the tree from the root to the leaves, building up a partition as we go. Whenever we reach a true leaf, we'll print out that partition. Seems simple enough, if it's the case that the branches of this tree is empty and the root value of the tree is true. Then I'd like to print out what you get by joining together the partition that I've built up so far using plus. Otherwise, if there are branches on this tree, then what do? Well, we get the root of the tree, which is the number m, because we put it there, right when we were creating the partition tree in the first place. We get the left and the right branches, which are the branches of the tree. Then we need to print out what's in the left branch. The left branch is the one that does include an m. So what we'd like to do is recursively call print partitions on the left branch, adding m to the current partition. I'd also like to print the partitions of the right branch without adding n to the partitions, because the right branch was no. So if we now print the partitions of the partition tree that you get for 6 and 4, we should see all of the different options: 2 plus 4, 1 plus 1 plus 4, 3 plus 3, etc. Whenever we reach a successful leaf, we print out the partition that we've built up. Otherwise, we pass in bigger and bigger partitions, adding an m whenever we take a left branch, and not adding an m whenever we take a right branch.